Hello. So today we are looking at this problem called maximum subarray. And the problem basically says that we have an array of integers called nyms, and we want to find the contiguous subarray containing at least one number. So let's see how can we solve this problem. So basically we want to find the contiguous subarray that contains at least one number that has the largest sum, and we want to return just that sum. So for example, for this array, the largest contiguous sum is 6, which is the sum of this contiguous subarray here. And as a follow-up, it says that if you haven't figured out the open solution, try coding the solution using divide and conquer approach. So what is the non-open solution though? So the one way we can solve this problem is just given an array like this, we could just do the simplest thing, which is just go over all the contiguous intervals, which means we'd go through this and then this and then this and do all of them until the biggest one, and then we will advance the pointer and do this one, and then do this subarray and do this subarray and continue all the way to the end and go to this value and start also doing this, then this subarray, then this subarray. You get the idea. We'll do all of them, but that would be open squared because we are doing 2 loops. So that's not good. That's a very straightforward solution, but I'm not going to code it here since it's not performant at all. So what can we do better? So we can use dynamic programming here to solve this problem. So basically, with dynamic programming, the first thing we need to do is determine the DP state, which is just you need to define in terms of like a subproblem. So we need to find a subproblem that when we combine all of the subproblem solutions, we can find the final solution. And so what is our DP state here? It's the sum ending at I. You might think that another way you might think first about doing this is say sum starting at I and ending at J. You might think of doing this, and so your DP, for example, of basically would be basically the sum of the numbers between I and J. The problem with doing this approach is it's hard to find it's hard kind of from this solution here to find like a DPIJ and find what is DPI minus 1 J, like what is this in terms of these values. It just gets complicated. So a simpler version is to think about this. So whenever you have a dynamic programming problem on an array, think in terms of either it could be like a suffix. So then it can be, for example, sum starting at I only, or it can be, so a suffix is our case here. It could be a prefix. So in that case, for example, it could be a sum or some function starting at some index I, or a suffix like what we did here, or it can be like a well, I'm going to call it a substring, but it's not really a substring. It's like in a range, something in a range. So these are usually you need to think about each one of them, which one of them is more convenient to use. In our case here with this problem, this is more convenient. So if we have the sum ending at I, then can we write this in the other step? Then the other step to do is here is to find the recurrence relation. So this was step 1. Step 2, base case. And then step 3 is to find the recurrence relation. So what is the base case? The base case here is for DP of 0, which would be basically, what is this? Let's just write it in terms of the state. This is the sum ending at 0. So ending at 0 means we have to take the element num0. We cannot leave num0 out. So that's the definition of our state. So basically that means that dp of 0 is basically the first element. Same thing for some. This is not our base case, but let's just, to find the recurrence, it's useful to just try to write some of them in terms of smaller values. So let's say dp of 1, we want to write it in terms of dp of 0. So dp of 1 is the sum ending at 1, right? Which can be either let's say the value at 1 alone. So either the sum ending at 1 is either 1 or these two, right? It can't be any other thing. It can be just -2 because that's not ending at 1. So it can be either these two or only this one. So either that or dp of 0 plus num of 0, right? And so we want the max, right? So at this point, we can just say dp of 1 is equal to the max of names of 1 or dp of 0 plus names of 0. And this actually applies to all i's here in this array. So for example, let's say at this position, it can be either this one with all of it, or it can be just this one, right? So at this point, we can just say it's dp of I is equal to the max of dp of. So it could be either this one or the max of all of these. So the max, which can be like a subset of the entire thing. Okay, so it's dp of I minus 1 plus names of I and names of I. All right. And so for this, we can just say, we can start doing this, right? So let's have n equal to length of the array. Let's define our dp array here, which would be 0 for the length of the array, which is n. And basically the max sum, let's just initialize it to be dp of 0. And dp of 0, we said it's this value here. And since we populated the base case for the value 0, we can just go through range just from 1 to n and do what we said here. And then just say max sum is equal to this new sum that we found and the previous max sum. And at the end, we can just return max sum. Okay, let's submit this. Okay, so that passes. One thing you can notice here is that we don't really need to have the entire array, because you can notice what we are using here is just the previous state, and we are creating a new state. So we can just keep one variable and then use that here and update it here. This is very useful when you have DP, is to look at which indexes of the DP array are you using. If you just are using the previous one and the current one, then there is no need to have the entire array. You could just have one variable and you can update it. And so here we could just get rid of this and call this current sum instead. And the previous value is this before updating, and the new value we can just update. And so here it's actually current sum, and that's about it. Let's see if this passes. It does. Okay, cool. So one other way to say, so the max also is, you could just say if current sum is negative, then don't add it. Otherwise, add it. That would amount to the same solution as here. So we could just say, instead of doing this max, we could just say it's nims I if the previous current sum value is less than 0, because if it's less than 0, that means adding it to this would just make it smaller. So it doesn't make sense to add it because we want the max. Else we could now add it, and so that would be this. And that passes. Okay, so this here is the same as Cadence algorithm, where we basically current sum is the max ending at the current position, and max sum here is like the max so far. You can Google Cadence algorithm, but this is the same way of thinking about it. And yeah, so if another way to make this solution shorter, it's not necessarily like better, it just makes it shorter to, if you want. So you could not have any of this, and instead of having like an extra variable, we can just put the values in the array itself, since we don't look at the previous value once we passed through them. So what we can do is, instead of doing this, just take the nims I, and that one would be nims I basically can be the max of. So either take the value, or so the same one as we did here. So let's just take this one. Except this time we are not doing DPI. We are putting the values in the array itself instead of using an O(n) like extra space. And so we could just do nums of I minus 1. And since we put the value here, we can avoid like doing this max sum each time, and then just at the end do the max of all the values in nims, since that's where we put the sums that we got each time. And that would be basically it. This is the length of. Okay, that passes. That's it for now. See you next time. Bye.